Unit 9 wave phenomena builds on Unit 4 waves, so throughout this unit we'll refer back to some of the concepts that we covered in Unit 4. In looking at 9.1 on simple harmonic motion, we're actually going to refer straight back to topic 4.1, oscillations, because there was some stuff that we covered there about simple harmonic motion, and in particular the conditions for simple harmonic motion to occur. So abbreviating simple harmonic motion to SHM, and what we saw in that scenario, and what I'm writing here is basically just rehashing that, so it's nothing new. Simple harmonic motion involves a restoring force, and there are a couple of things about that restoring force that are important to make note of. The first is that the magnitude of the force is directly proportional to the displacement. So that's the first point to note. And because it's a directly proportional relationship, we can express that symbolically. I'll do that once we've got both of these points jotted down. So to the object's displacement. So that basically deals with the magnitude of the force, and so we also then need to be concerned about the direction, because we know that force is a vector, and we can say that the force is always directed towards the equilibrium position. So again, just bringing this back to mind so that we're familiar with the concepts. Some of these terms, if you can't quite remember what they mean, so equilibrium position or restoring force, what those sorts of things are, make sure you go back and review those. Another way to consider the direction here is that it's always going to be in the opposite direction to the displacement. So there's another term, or another way to consider the direction of the force. So it's in the opposite direction to the displacement. So as I said, we can write a mathematical relationship here, or a symbolic relationship, and that would be expressed in the following way. So the force is directly proportional to the displacement, but it's in the opposite direction, so we can indicate that that's a negative there, and we should really indicate that we're dealing with vector quantities here. Now if we think about Newton's second law, so from Newton 2, using that abbreviation, we have that force is equal to mass times acceleration, and so because the mass is constant for this object that's going to be undergoing simple harmonic motion, what we can see is that the acceleration is likewise going to be proportional to the displacement and in the opposite direction. So we've got that relationship we can also express. That's a one that comes up a number of times in a few questions on past exam papers, so it's something to be aware of, so that you can apply that idea to a range of different representations, whether it's graphically, whether it's substituting into equations, or whether it's just explaining the concepts of acceleration, displacement when it comes to simple harmonic motion. We'll actually develop that a bit further in coming videos to look at the relationships in terms of equations rather than just this proportional relationship. We also had a look at graphs of simple harmonic motion, and in particular that graphs of simple harmonic motion have a periodic nature about them, and that means that we can express them mathematically as well. In Unit 4 we didn't go into the detail about how we would define them as an equation, but we'll do that here. So if we look at a graph of simple harmonic motion, so just sketching one here quickly, horizontal axis will have time, and the vertical axis we're going to have the displacement. And we saw that it had this periodic shape, so increasing and decreasing as the object was oscillating backwards and forwards. Now The general form that we're going to deal with here, so this is now new information, not covered in Unit 4. The general form of a periodic function, you may have seen this in maths, and we'll hopefully just build on your understanding of periodic functions from maths. In this particular case, the general form, we'll write it as x is equal to a sine bt, I'll put that in brackets just to make it a bit clearer, plus c. Now those quantities relate to specific aspects of that graph. So a has to do with the amplitude, so how tall or how the distance between the peaks and troughs. B relates to the angular frequency, and C is a I'm going to put it in inverted commas here, a vertical shift. What we mean by vertical is if you look at the graph, the value of C would sort of mean that graph sort of would sit up here somewhere instead, so it sits above the horizontal axis. In the case of what we're dealing with simple harmonic motion, we'll see that will always be 0. To relate this directly to simple harmonic motion, the amplitude that we're going to deal with, so the value of A, we're going to call x naught, and that relates to the maximum displacement, otherwise known as the amplitude, but given that we're using the value x, it just makes it a bit clearer that we're dealing with the maximum displacement. B is angular frequency, and the symbol that we use there is the Greek letter omega. It sort of looks like a W, but it's a little bit more sort of loopy. We'll talk about that in a bit more detail in the next video. And as I said, the value of C here is going to be 0, and that's because we're dealing with oscillations around the equilibrium position. So we will never see any values of C being anything but 0. That means that we can simplify that equation or represent it more specifically in the context of simple harmonic motion in this way. So x is equal to x naught sine omega t. I'm going to highlight that one because that's in the data booklet. It's one that you need to be aware of. Note that we're using a sine function here purely because the graph that I drew above was a sine function. It started at the origin. Alternatively though, it might be that you don't start timing the motion of simple harmonic motion as it passes through the equilibrium position. It might be that at time t equals 0, it could correspond to the value of x being equal to x naught, in which case we're not dealing with a sine function, we're instead dealing with a cos function. So we could instead write that would be x is equal to x naught cos omega t. So either of those two expressions is fine. In the end, we're dealing with periodic functions, so a cos function and a sine function are basically the same thing, just a bit of a phase shift. But just be aware that you can represent a periodic function using either of those two. And we'll continue to develop that, as I said, looking at velocity, acceleration, and relating all of those equations together. And we'll do that in the next few videos.